In this lesson, we'll see how to solve exponential and logarithmic equations. Recall that both exponential and logarithmic functions are one-to-one, so we can use this property in solving equations by saying if the values of exponential function with base b are equal, then the inputs are equal. So really what we do, we drop the base and we end up with comparing the inputs. Similarly with logarithms, the values of logarithmic function with base b are equal, therefore the inputs are equal. Again, we can drop logarithms from both sides as long as they have the same base and as long as it's single logarithm on each side. So we can't have any addition or subtraction. We can't have two logarithms on any of the sides. It has to be a single logarithm and then we can drop it. Let's start with some examples. In example A, we have exponential equation to solve. What we can do here is to try to make the right-hand side a power of 2. So to keep the same basis in order to drop them later on. So rewrite 16 as 2 to the 4. Copy the left-hand side. And now using the first property, we can drop the base 2 and we end up with just 3x minus 5 equals 4, which is a linear equation easy to solve. X would be, we add the 5, which is 9, and we divide by 3, so overall is just 3. So this is very powerful method, dropping the base as long as it's the same base. Let's try the second example. Again, we're trying to get each side in a form of exponent of the same base. So on this side, we can combine the two powers because we have the same base 3 by adding the exponents x squared plus 4x. On the other side, we can express 1 over 27 as a power of 3. Since 27 is in denominator, this power of 3 must be negative. And 3 to the 3 is 27, so that will be 3 to the negative 3. Now we can drop the 3 as before, just because we use the one-to-one property of exponential function, and we're saying that this equation is equivalent to x squared plus 4x equals to negative 3. We can bring the negative 3 to the other side as positive 3 equals 0. So we really need to solve quadratic equation of this type. And this can be solved by factoring. X and x, product 3, so 3 and 1 should work, and sum 4, so plus 3 plus 1, yes, that works. Therefore, our solution is negative 3 or negative 1. There's two solutions this time. And next example, here we have power of 8, on the other side power of 16. Well, we can't bring 16 to 8 easily. However, we could change both bases to a new base, base 2. Since 8 is the same as 2 to the 3, and then is raised to the x, we multiply 3 times x. And here 16 is the same as 2 to the 4. But then it will be multiplied by the existing power, 3x plus 9. Now we are ready to drop the bases and compare just exponents. 3x equals, we can perform this multiplication, 12x plus 36. And again, it's a linear equation, it's not difficult to solve. Subtract 3x, that will be 9x, bring the 36 to the other side, and divide by 9. So we end up with negative 4. Again, we have one solution. One more example, this time logarithmic equation. Since I have a logarithm on one side and a constant number on the other, I can use directly the definition of logarithm, which translates whatever you see here into exponential form by saying 2 to the 5 equals the input. So 2 to the 5 equals 7 minus 6x. And again, that's a linear equation easy to solve. Bring the 6x to the left. 7 minus 2 to the 5 is 32. So we have x equals negative 25 over 6. Here we have more examples. exponential equation, but this time both bases are different and it's really hard to bring them to the same base. So the strategy in such case is to bring the exponents down by applying any logs. For example, put ln on both sides. So we have ln 3 to the x plus 2 equals ln 5 to the x minus 1. And then the property of ln allows us to drop the exponent down in a bracket times ln 3, which is certain constant. Similarly, on the right hand side, drop the x minus 1 times ln 5. Okay, so now we see a linear equation and we want to collect x's. So in order to do that, we actually need to multiply the bracket through the ln 3 and ln 5. So it will be ln 3 times x plus 2 times ln 3 equals ln 5 times x minus ln 5. Now we want to collect terms with x's to one side and free terms to the other side. So after bringing this term to the left and factoring the x out, we have ln 3 minus ln 5 x equals negative ln 5 minus 2 ln 3. Finally, we divide right hand side by the bracket and we end up with x equals whatever we have here, but we can rewrite the right hand side in slightly different form. We can, for example, pull the minus out of the bracket and then bring the 2 as an exponent for 3 inside the ln. So we have ln 5 plus ln 3 squared, it's 9, over this bracket ln 3 minus ln 5. So this is already a good answer, it's an exact answer, but we could simplify this even further, saying this is negative and ln 5 plus ln 9 is like ln 5 times 9, so it's ln 45. In the bottom, we have ln 3 minus ln 5, so it's the same as ln 3 divided by 5, but 3 divided by 5 is like 0.6. So it's ln 0.6. And that would be the exact answer. However, we could approximate this as well using calculator. So after you plug it in this expression to your calculator, you should end up with approximately 7.452. And another example, logarithmic equation. We can put together these two logarithms as a single logarithm. Remember, we can drop logarithms only if there's single logarithm on each side. So, because that was minus, it translates into quotient of inputs under single logarithm. And here 2, well, we could leave the 2, or we could rewrite log 4 from 4 squared, because log 4 cancels the base 4, so it's really the same as 2. And now we can basically drop the log from both sides and compare the input. X plus 3 over x minus 5 equals 4 squared, which is 16. To solve this equation, multiply by the denominator. We have x plus 3 equals 16x minus 5 times 16 will be 80. And that's a linear equation. So bring the x over, that will be 15x, and plus 80, so it's equal 83. Therefore, x by itself is 83 over 15. And we have exact answer. The next example is quite interesting. We have 3 to the x, then a free number, and on the other side, a coefficient times 3 to some other exponent. Well, in this case, the strategy is to multiply the whole equation by 3 to the x. Why? Well, we want to get rid of this negative in the exponent. So if we multiply by 3 to the x, we'll have to add exponents, which will turn out to be 0. so we won't have negative exponent anymore. Let's multiply. 3 to the x times 3 to the x is 3 to the 2x, or 3 to the x squared. Then we have negative 8 times 3 to the x. And finally, let's rewrite this term to the left. It will be plus 15. And now 3 to the negative x times 3 to the x is actually 3 to the 0, which is 1, so we don't really have to write this. Well, notice that what we obtained is actually something reducible to quadratic equation. It's enough to replace the 3 to the x by some other variable. For example, let a be equal 3 to the x. So now in terms of a, we really have equation a squared minus 8a plus 15 to solve. And we know very well how to solve such equation by factoring. Well, we factor a minus 5 and a minus 3. So the product is plus 15, the sum is negative 8, everything works. Therefore, our a is either 5 or 3. But we're not solving for a, we need to solve for x. So now let's come back to the substitution equation and solve for x. A is the same as 3 to the x. That's 5, or 3 to the x equals 3. So to solve for x in the first equation, we apply ln on both sides, and then we can drop the x times ln 3 equals ln 5. Therefore, x by itself is ln 5 over ln 3. So that's exact answer. Notice that this really means the same as log with base 3 from 5. But for the sake of calculation, this answer is even more desirable. Or the second equation produces pretty easy answer, because this is 3 to the x, this is 3 to the 1, we can drop the base, therefore x is equal to 1. So either 1 or log 5 over log 3. Next example is the composition of two lawns. So ln of ln. How to reach the x? Well, we need to undo this function of ln by placing e underneath on both sides of the equation. So this e will cancel the first ln, and we're left with just single ln x. On the other hand, we have e to the 5, whatever that is. We are already closer to x, but we still need to get rid of this ln. So let's do the same trick again. Put e underneath, and then e cancels the ln, therefore the x by itself is e to the 5. And if you want to have some sort of idea what is that number, you can plug it into the calculator. However, remember that your exponent for the first e is actually e to the 5. Altogether, you should end up with a number 2.85 times 10 to the 64. So it's a really large number. Notice that this expression is not the same as e to the e and then to the 5. That's not the same, because this would mean the same as e to the 5e. And over there, we really have e to the, and then the exponent is e to the 5. So when you enter this x to the calculator, you should key in e to the exponent, bracket, e to the 5. Close the bracket, equal. The next example involves lawns on both sides, but the use of 2 is different. This 2 on the right hand side is a square of the value of lawn. However, 2 on the left hand side is a square of the input, and then lawn is taken onto it. So on the left hand side we can drop the 2 down before the ln. While on the right hand side we can't really do anything. So let's rewrite this. And now observe that if we let ln x be called a, that means replace ln x here and there by a value a, we really end up with the equivalent equation of the sort 2a equals a squared. What would you do with this equation? Well, I would bring everything to one side and factor it. So let's do the same with the ln equation. If we bring everything to one side, ln x squared minus 2 ln x equals 0, and then factor ln x, then inside we have ln x minus 2 equals 0. So there is two possibilities, ln x equals 0 or ln x equals 2. To solve the first equation, if you place e underneath on both sides, we end up with x equals e to the 0 is 1. Or, to solve the second equation again, place e underneath, and we have x equals e squared. So we have two solutions, either 1 or e squared. And the last example of this type, it's an exponential function, but it's kind of complicated. It has division, it has 4 exponents with positive or negative exponents, so that's quite a bit of work. What to do first? I would suggest to multiply by denominator to the other side. So multiply by this expression first. We'll end up with e to the x plus e to the negative x equals 3 times e to the x minus 3 times e to the negative x. Then what we could do is to collect terms with e to the x on one side and e to the negative x to the other side. And in the meantime, we could factor the common e to the x. So e to the x, 1 instead of this term, and then minus 3 instead of that term. Now, if we bring the e to the negative x to the other side and factor it, we have negative 1 and negative 3. So altogether we really have negative 2 e to the x equals negative 4 e to the negative x. Now what we could do is divide the whole equation by e to the negative x. So we end up with negative 2 e to the x over e to the negative x equals negative 4, and e to the negative x disappear because it was divided by. Now we could divide by this negative 2 to get rid from the left-hand side, as well as combine the exponents, because then we'll have the same basis, so it's e to the x minus negative x, so it's 2x, equals negative 4 divided by negative 2 is just 2. And finally, we could apply ln on both sides of the equation to bring down the exponent. So this is equivalent to 2x equals ln 2, which is the same as x equals 1/2 ln 2. So that would be the final solution. And here we have another equation to solve, but this example will show us that it's very important to check the possible solutions against the domain. So like in previous questions, we've got, for example, here two solutions, 1 and e squared, but are these solutions in the domain of the original equation? Yes, they are, because they are positive. And the domain here was everything that is positive because of ln. Right? So yes, they've been okay. But for example, if we would end up with some negative number, if this would be negative 1, we wouldn't be able to take it because of the domain of the equation. Therefore, make sure that you always check against the domain of the original equation. Let's try to solve this. Let's put together ln's, because remember we have to have single ln's on both sides in order to drop them. So when we put it together, it will be ln 3x over 4 equals ln x plus 1. Now we can place e underneath on both sides in order to drop the ln's. So we end up with 3x over 4 equals x plus 1. Let's solve it, multiplying by 4. Bring the 3x to the right, so it will be just 1x equals negative 4. Okay, we do have a solution, but is that a good solution for the original equation? Let's check against the domain. But what is the domain? Maybe we should state it. Domain of our equation is, we need to make sure that 3x is positive. That means x is positive. So one condition will be x must be positive. 4 is always positive, so it's okay. But secondly, x plus 1 must be positive, because that's another input for ln. This condition is equivalent to x is bigger than -1. So if I have something bigger than -1 and bigger than 0, obviously the stronger condition is bigger than 0. So this will be the overall domain from 0 to infinity. Okay, but -4 is not in domain, so it has to be rejected because it's not in domain. Therefore, the final solution to this particular equation will be no solution. This time we have no solution. Equations involving exponents or logarithms sometimes are too complicated to solve it algebraically. This usually happens when, for example, we have x's in two different levels, in the base and in the exponent. It can't be solved algebraically. Then what we do, we can just approximate solutions using graphing calculator. So we need to be able to do that as well. We can do it in two different ways. For example, plug it in the left-hand side under y1 as a first function, and the right-hand side under y2 as a second function. And then try to find the intercepts of these two graphs. The x-coordinate of those intercepts will be our solutions. So the graph looks somehow like this. X squared is a parabola. 2 to the x will go somehow like that, and then grows a lot faster than x squared, so we'll have 3 points when the two curves intersect. So the x-coordinates of those points will be our solutions, x1, x2, and x3. I plugged in 2 to the x and x squared, and I'm going to use this window, -2.5 till 5 and -2.5 till 20, to see clearly our two curves. And as you may notice, here we have one intersect, second intersect, and third intersect. And then in order to find those intersects, it's enough to go second calc, intersect, number 5. The calculator asks us for first curve, you say yes, enter, second curve, yes, enter, and the guess. Well, let's scroll first to the left-hand side, to the first root, enter, and the intersection is given as -0.767 when you round it. Do the same with second root, again intersect number 5, first curve yes, second yes, your guess closer to the intersect, somewhere here, enter, and we have intersect at 2. Finally, the third one, number 5 again, first curve yes, second yes, scroll it closer to the intersect and enter. Yes, we have 4. The second approach would be to bring everything to one side and treat this as a single function and plug it in under y1, just 2 to the x minus x squared. So we're really comparing this with 0 when this is equal to 0. So our function will look somehow like this, and we're looking for the 3 zeros, this one, and that one. So those will be our solutions to the original equation. Plug it in one formula, one function, highlight this and unhighlight the previous ones, graph it, and as you see, again, we have 3 points. Now to find those points, second calc, 0, number 2. We scroll before the 0 here, we don't see very well, so actually it would be nice to get different window. So I want to see a little bit more on y-axis, so let's say -5. Okay, second calc, 0, which is number 2. we scroll the point before the 0, has to actually cross the x-axis after the 0, and enter again for the guess, and yes, the same root. You can check the other two roots, it goes the same way. You will expect those roots to be 2 and 4. Those points turn out to be, those are the same as here, x1, x2, and x3. They turn out to be approximately negative 0.767. This one turned out to be 2, and that one will be 4. So we have three solutions, 2, 4, and a fractional negative number. Well, with 2 and 4, it's very easy to check. 2 to the 2 is 4, 2 squared is 4, so yes, that's a solution. Similarly with 4, you can check on your own. Let's try to solve this equation by yourself. So use your calculator, plug it in either the first way or the second way, and find the solutions. For the second equation, we have function ln x plus 1, and I brought the right-hand side to the left, creating one function, minus 2x plus 3. Let's graph it. Oh, we see two possible zeros. Let's check the second one because we can see it easier. So second calc 0, number 2, before, enter, after the possible 0, enter, and enter again. Here's our 0, 2.059. For the first 0 though, we wish to see a little bit more clearly this part of the graph. So we need to change the window again. Maybe x doesn't have to go any farther than 0, but the y value needs to be closer to 0. So negative 1 to maybe 5. We are closer here, but this is pretty vertical, so still we don't see this. Let's use zoom box, number 1, and then we establish where do we want the box to be by arrows, enter, and draw the box again using arrows so we can actually see just this section that we are interested in, and enter. Oh, here the curve crosses the x-axis, so we are fine. Use second calc 0, number 2, and we need to scroll before the 0, which is from the left somewhere here, after the 0, enter, and enter again. The 0 is negative 0.993. Try this on your own, please. The solutions turn out to be approximately 2.059 or negative 0.993. And we have one application problem. A yeast culture grows according to the equation, and here's given equation. As you may remember, this looks like a logistic pattern, where P is the number of yeast and T is time in hours. Graph function P of T for T bigger equals 0. Well, to graph it, you can use graphing calculator and find out the shape. Okay, we wanted to graph this logistic curve, 50,000 divided by, make sure that you use a bracket for the denominator, 1 plus 250, and then it's e to something, again, it has to be in a bracket. We can put another bracket here. So now we need to extend the window quite a bit. So let's see. Let's draw it from maybe negative 10. Go up to maybe 50. Then y-axis, we can start from negative 100. And we can go up to 60,000. So we can see 50,000 clearly. Graph. Okay, the graph looks like that. Notice that this curve doesn't really start from 0. If we zoom this section, you will see that it's higher than 0. Obviously, you can plug it in 0 into your expression, and then it will be 50,000 divided by 251. So you can check on that 50,000 divided by 251 is a little bit less than 200. So this number is tiny bit less than 200, but it's definitely not 0. It's just because the scale is so large. That's why we don't see this clearly here. So the shape turned out to be approximately like this. as we may expect, logistic curve. For t bigger equals 0, it starts above the x-axis and it stabilizes at certain level. It would be nice to find out what is this level. Also, you could find out this point just by plugging in 0 to the formula. Now, the next part of the question asks us to estimate the number of hours before the yeast population reaches 35,000. You can probably predict, using your calculator, that this limiting value is actually 50,000. Check it on your own. And the population will reach 35. Well, let's draw the level 35 somewhere there. We are interested in t value. Let's call it t1, because that's t and that's p. We are interested in such value t1 that the graph reaches 35,000. When the level 35,000 bacteria will be reached. So what we really need to do is to plug it in another function, 35,000 as a constant function, and graph both of them, and then find out the intercept of these two curves. So second calc, intercept, which is number 5, first curve, second curve, guess, and we have the intercept 20.9 when we round it. And we found that that number is approximately 20.9 hours. So it has to pass nearly 21 hours in order for the population to reach the 35,000 count. And t is about 20.9 hours. Estimate the horizontal asymptote. If we want to find out the horizontal asymptote, it's a good idea to maybe trace the function. So trace that function, scroll it, and observe the y value. The y value, when I go more and more to the right, appears to be approaching 49,900, 49,99, nearly 50,000. It doesn't cross the 50,000 level. It stabilizes at that level, but it's very, very close. Yes, it's 50,000 because the calculator doesn't distinguish between pixels anymore. So horizontal asymptote appears to be 50,000. That's the capacity of the population. Well, we figure out that the horizontal asymptote has the equation P equals 50,000.